Alright, so for this one, we have a microwave. We're microwaving our spaghetti. We have 0.4 kilos of spaghetti. That's a pretty good bit of spaghetti. And its temperature rises by 45 degrees in 120 seconds. The question is, what is the power absorption by the spaghetti? Well, power is energy delivered over time, right? And so, first question is, what is the energy delivered to the spaghetti, which is the heat change in the spaghetti, right? MC delta T, where this M is the mass of the spaghetti, the C is the specific heat of spaghetti, and the delta T is the change in temperature. So we have 0.4 kilos. We have 3.76 times 10 to the third joules per kilogram. Joules per kilogram degrees C. Alright. And we have delta T of 45. 45 degrees C. Alright. So 0.4, 45, 3.76 times 10 to the third. 0.4, 3.76 times 10 to the third. And 45 degrees. Total heat is the product of all of these. Right? Alright. So 6.77 times 10 to the fourth joules. That's how much heat this absorbed. Now we need to know the power. Well, the power is, in this case, the amount of heat absorbed and divided by the amount of time it took to absorb that heat. So 677 times 10 to the fourth joules, all divided by, get some brackets in there so this works right, all divided by 120 seconds. Right? So, back over to Excel, 120 seconds. So the power is that divided by that is 5.64 times 10 to the second. 5.64 times 10 to the second joules per second. And a joule per second, I'm going to make this 564. Right? 564. A joule per second is a watt, so this is 564 watts. Alright, now part B. Find the average intensity of the microwaves. Okay, so we have power. We have the area of the plate, which is given by its radius, right? Radius of 10 centimeters. So intensity is power divided by area. So in this case, the 564 watts divided by pi, radius is 0.1 squared, right? Pi r squared. Okay. So equals that divided by pi divided by 0.1, well, 0.01, yes, 0.1 squared, 1.8 times 10 to the fourth, 1.8 times 10 to the fourth watts per square meter, which is units of intensity. And down here in the denominator, we actually have meter squared, right? Alright, so that gives us part B. Part C, what is the peak electric field strength of the microwave? Okay, so we have the intensity, and once we have the intensity, we just go to our handy little equation that is I equals 1/2 C times epsilon naught times E naught squared, where C is the speed of light this time, not the specific heat of the material. Epsilon naught is permittivity of free space, and E naught is the peak electric field strength. All right. So if we're going to solve this for E naught, this would be E naught equals square root of 2I divided by C epsilon naught. Epsilon naught. All right. 2I divided by C epsilon naught. We have I. C is 3 times 10 to the 8th meters per second. Epsilon naught, let me get that from, right here, 8.85 something. It's not opening for some reason. Give me just a second. Okay, so we have epsilon naught is 8.854 times, 8.8554 e to the minus 12, right? That's epsilon naught. 8.854 times 10 to the minus 12 coulomb squared per Newton meter squared. Okay, we have the speed of light, 3 times 10 to the 8th. Okay, and so we're looking for the intensity, twice the intensity, right, which is 1.8 times 10 to the 4th, twice the intensity divided by C divided by epsilon naught, all square root, equals square root of 2 times the intensity divided by epsilon naught divided by the speed of light. 76.6. We're just going to go with 3680. All right, 3680. volts per meter. Okay, and then part D. What is the peak magnetic field strength? Part D is pretty simple and straightforward. E over B equals the speed of light. Right? So B is going to be E over the speed of light. Alright, back to Excel. There's our E divided by the speed of light. Gives us 1.23 times 10 to the minus 5th Tesla. And that's it for problem 2.